Hi, this is Parisa. We are going to learn about CNNs. It shouldn't be such a big deal. So we import some useful libraries: TensorFlow, Keras, Matplotlib, and NumPy. So we want to classify MNIST dataset. It has 10 different digits written by different handwritings. They are 60,000 samples for training and 10,000 for testing. Each sample is an image of handwriting 28 by 28, and they're all saved in mnist.load data, and mnist is in the keras.dataset package, so we don't need to split it. It's already split, and we define some initial parameters: batch size, number of classes are 10 because the digits are from 0 to 9, which makes 10 digits, 10 different classes. And the number of epochs, I want to increase it because it's very small. One is not acceptable. So when we load the images, the arrays of the image are flattened. We want to bring back all those flattened parameters together so that it looks like an actual 2D image. So we reshape it um, using these columns and rows that we want, both X train and X test, and we want to see how it affects the input shape. So previously it was um, it looks like it's already 28 by 28. So whatever. And we are just plotting the 10 the 16 first samples of the training data set here by this loop here that says for the 10 first numbers 0 to 10, just uh, draw a grayscale of x of train I, which I ranges from 0 to 9. That makes the first 10 samples in the training set to see. And here we want to design, let me see if I ran everything. Yes. I want to design the architecture of the model set in the description. So we want sequential convolutional neural network. It starts with a convolutional it's 2D because we're using images that are 2D, that we're using 32 filters in the beginning with kernel size of 3 by 3. The kernel is going to move on the 28 by 28 image to provide the convolution result, and the activation function is ReLU. Input shape is given by has been defined previously here up here. So we had input shape defined by number of rows, number of columns, but also because channels are considered in images, and colored images have three different channels, for example. We define one, so it's actually 3D, but the third one is the number of channels, which in this case is one, because we have grayscale images and we don't have like other channels for that. So that's the input shape, and then it's so we define input shape always in the first layer. um, um, but that the remaining layers, they don't need input shape because they're followed by the previous, and they can like take care of it by themselves. So it follows by a convolutional 2D layer 64. Filters, this is the size of the kernel. Again, the activation is also ReLU, and the max pooling 2D tries to takes out features from convolution layers by taking pooling, max pooling. So it takes windows of 2 by 2, moves it across the result of this output of this convolution layer to take the maximize of each 2 by 2 tile on the image, take the maximum value for each for the 4 pixels available there, and puts it in there. So after this convolution layer here, the max pooling applies, we will have significant change in the dimensionality to get features out of the image. And the dropout layer here is to, so we're getting rid of like 25% of connections, so that everything is not in full connection, um, so that we bring down the confidence of the network, making it deal with overfitting later. Uh, and we use flatten to turn the 2D um, to the output of this dropout layer. So up to here, everything was 2D. We're flattening it because we want to apply dense layer to it. Dense is fully connected, and we want to get to a flattened output. Number of classes are 10, and change from 0 to 10, so it's flattened. It's not an image anymore. So we need to flatten it and add a dense layer to it by a 128 neurons in the hidden layer, and the activation is tilt ReLU, and again followed by a dropout to take care of the overfitting and bring down the confidence. At the end, there is another dense layer that maps all the outputs, maps whatever happened, all the features taken from these previous layers, um, to the number of classes. So it clearly gives us what class it belongs to. And the activation is softmax, which gives us an output similar to the probability of this output belonging to a certain class. So it's a value between 0 and 1, and that probability help us decide. And I ran this so we can see the summary. It shows how these layers affect the shape of the output. So after it was 28 by 28 after conv2d, the first conv2d, because the filter size is 3 and the stride is 1, so we will have 28 minus 3 divided by 1, which gives us 25, and at the end adds 1. And I cannot discuss the details in here. I'm running out of time, but you can see the calculations why it the output would be this size, and 32 is the number of filters that makes the number of channels of the convolutional layer, and then followed by another convolutional layer. Again, for the same reason, it becomes 24 by 24, and 64 is the number of channels. Again, filters, yes, number of channels defined for the convolutional layer. And as you see, the max pooling drops the dimensionality to 12 by 12 by 64 because of number of channels. Dropout has the same dimension, doesn't affect the dimension, and just zeroes out some weights to bring down the confidence. It doesn't affect the convolution. And 9,216 is the multiplication of these values, so it flattens it and then maps it by applying the dense layer. It maps the output to 128, and so dropout doesn't change the dimension, and at the end we want 10 distinct outputs, so it maps the dense layer maps 128 to 10 outputs. And by these values here we can see how many parameters are in the system, and the total number of parameters are 1 million, which seemed to be a big number. But if we've been using a dense layer instead of convolution here, it was even much bigger than this. If you see, dense layer is responsible for the most number of parameters in this network because it connects all of the neurons fully to each other. So, and here we are doing compiling the model, training it, and then evaluate it. So compile defines some initial values like the losses. What would be the loss? It's categorical cross entropy. Cross entropy is good loss functions for classification. Is recommended in most cases. And categorical means that it's not binary. So we have binary cross entropy and categorical. Here is categorical because we have 10 distinct classes, not just two. But binary classification is also very common, so we have that one as well. And the optimizer here is Adam. The explanation is out of the scope of this video, and the metric is accuracy. I'm wondering why the learning rate hasn't been defined here, but it can be. So you can define an initial learning rate here, and it says that so it calculates the loss, like the difference between the output of the system and the desired output, which gives us the loss. This is the way it is calculated by this formula, and then to minimize that loss, uh, to get the output of the system similar to the desired output, we need an optimization algorithm. So here, Adam is used for that. And the metric of accuracy mm, shows this optimization is applied on what metric, like, um, and what metric is being shown at the end. So after minimizing the loss, we want to see how it affects the accuracy of the model, and that we want to get feedback from that side. So we compile it, giving it these initial values, what we need for our network, and after finalizing it, we can fit the model by giving it the train X and train Y. X train includes the 60,000 different handwriting images, 28 by 28, and Vitrain includes the values of what each of these images, what they represent, what digit. So it can be 1, 2, 3, 0, whatever, depending on the image. So the model is trying to find a modeling between these the input and output of the train, so that by completing the modeling, applying this model on any other unseen data gives us the correct classification. The batch size is used to load images in smaller batches. So we have 128 batch size, that it loads 128 by 128 to kind of increase the memory usage, gets better use of memory, and it has its own benefits. Until it reaches like the number of all the data samples, that in this case are 60,000. So 128 by 128 by 128 until we load all of 60,000. This is called one epoch. And after loading all of these things and applying the optimization, at the end we apply optimization, and we go through the so it's called a feed forward, and then it applies the back propagation after each epoch. And again, and after backpropagation, we have updated weights. So the weights of the CNN are updated. Now the should be closer. The loss should be closer to zero, meaning that our output is more similar to what we expect. And again, another epoch makes us make progress. So so I want to train with 100 epochs to show how that affects the accuracy. So metric is accuracy, it shows us later. And then we evaluate our model, we test values. There are 10,000 samples for testing. I would rather have this one. And okay, one important thing is that don't make my same mistake. But yes. don't make my mistake. And before doing anything in the Colab, if you're using Google Colab or any other machine that has access to GPU, please switch to GPU before starting calculation because it takes a lot of time if you don't. And so I'm going to rerun everything. It shouldn't take much time. And as yes, we want to. So it asks you to restart everything and rerun. Better to say restart and run all. Yes, when you change it to GPU. Okay, what's going on? Keyboard interrupt. Okay, it's going ahead. And at the end, after oh, we're not plotting anything here. We should have, like, we can plot the changes of the accuracy to see how training affects the results. Yeah, I switched verbose to one. It shows us more information on the training. So even if we are not plotting, let me close this. Even if we are not plotting, so look at this, it's going slowly by slowly. It's because it is loading different batches, and at the end it ends one epoch. So you can see the loss value. Here is the loss. Oh, and the accuracy. Okay, let me. So these are the values for training. It's showing us the values, but as we loaded, yes, these are training values, but after finishing the training, we are saving the evaluation on the score and we can actually plot it. So we can say that plt.plot. I hope this helps. I usually don't use the evaluation this way, so I need to try it. I wish I wouldn't set the epochs to 100, but we can plot it here later. And then sometimes we finish training at some point, but later we want to continue on it, or we want to fine tune it on another data set or whatever. Or we want to use this model for other. We said that we want this modeling so that we can feed new handwritings to it, and it gives us as output if it can actually read that handwriting. So we need this model later. We need to save it somewhere so that we use it. And it's straightforward process. Model.save my model is the name of it. Usually it's common to add H5 format at the end of it, but it can have any name and you can give it another address, like go to a certain folder or whatever. Here its name is my model. You can call it A5 CNN. That is the name of this project. And then later when you want to load it and use it, you load it this way: keras.models.load model, and then you call this name in here. It loads it for you. Oh, yeah, this is just printing. It's not plotting anything for you. And then you can see that it can actually load the values. And we can also plot it here if it works here. We can plot it later here. So because I really need time, and I'm running out of time, and I don't want to I really don't want to use my delayed uploading. So I'm stopping here, but in the next assignment, at the end of next video, I can show you the final output of this. Have a good one.